All right, so we're going to start chapter 10, and chapter 10 is basically kind of like a continuation of the previous chapter, chapter 9. We're hypothesis testing, but this time on two samples. So let me give you a little bit of background. If you remember chapter 9, we were basically testing if the mean is equal to some number, some random number out there. Now we're going to test if two different groups have the same average. All right. Now, obviously, there's some pretty blatant, obvious reasons that you would want to do this. For instance, um, we might want to test if two groups of people are, have the same average, or if a trait is equally distributed amongst two sets of people. All right, or any two sets. It doesn't have to be people, obviously, but it can, most of the time in this class, we'll talk about differences between groups of different people. A second, and probably just as equally powerful thing we want to talk about, is we want to test differences on effects of, for instance, control and experimental groups. So we have a control group, we're doing an experimental study. We have a control group, an experimental group, and we want to figure out what's happening if there's any effect at all. So there we go. Now that's going to change our null and alternative hypotheses. Our null hypothesis, since we're testing if groups are having the same average, our null hypothesis is going to be the average of group 1 is equal to the average of group 2. And our alternative hypothesis is going to be the average for group 1 is not equal to the average for group 2. So generally speaking, we use these little subscripts to denote group 1 and group 2. And so the population average for group 1 is equal to the population average for group 2, or alternatively, the population average for group 1 is not equal to the population average for group 2. And just like in the previous chapter, we can have less than, greater than, or not equal as our inequality sign for our alternative hypothesis. Now, this is going to look really familiar. Last chapter, we had an outline that used a z-test, a t-test, and a proportion test. Well, in this chapter, in a very similar way, we're going to have what's called a two-sample z-test, a two-sample t-test, and a two-proportion test. So we're going to have these same sort of structure for testing. Now, z-test, well, since we have two groups, in order to have a z-test, we're going to have to know both groups' population standard deviation. And in order to have a two-sample t-test, basically, if we have one of the standard deviations of the populations which is unknown, we have to use a t. So let me make that clear, because I wrote both standard deviations of your sample are known. Most of the time, we're going to have sample standard deviations. So again, the t-test is slightly more common than the z-test. I said that in the last chapter. But even if I have one group's population standard deviation and one group's sample standard deviation, I still have to use t. All right? And then obviously, we're going to use a two-prop z-test for proportions. Now, we're actually going to add one more test here, and that's the test that utilizes paired data. And when we have paired data, we're going to go back to our original t-test with data. So we'll get to that more once we get to it, but there's essentially 4 tests here. So there's the two-sample z-test. That's when I know both population standard deviations. There's the two-sample t-test. That's when at least one of the population standard deviations is unknown. Most of the time, we're going to have both sample standard deviations on that one. and then a 2-prop z-test with proportions. And then that last one is the paired data with the t-test. So we'll get into each of these in just a moment. Now, I want to say something about what's going on sort of behind the scenes. The machinery that we're using here is still the central limit theorem. So it's still the central limit theorem, but it's a lot more detailed in terms of the mathematics that's going on. Because we have two means, it turns out we have to center our normal curve at 0 and assume that the difference between the two means is 0. Think about adding mu2 to both sides. You'd get the null hypothesis. So this is equivalent to the null hypothesis here. So it's a little bit more complicated. And just to give you a sort of insight into that, not only are we dealing with two means, but we're dealing with two standard deviations. So we make two means be the center of our normal curve by subtracting them and assuming that they equal to 0. If we were doing a z-test, we would do a standard deviation. It would look like this complicated thing. All right, so it's kind of, in one sense, averaging the standard deviations. It's not exactly, but that's what's happening. And obviously, these would be sample standard deviations if it were a t-test. For proportions, this is the new standard deviation. So you can see the mathematics behind the scenes are a little bit more complicated because we're dealing with two averages. Now, the nice thing is our calculator is going to do this all for us. So our calculator is going to do all the behind the scenes stuff, and it's going to give me out a p-value, and that's what I'm going to use just like I did in Chapter 9. Now, one thing I want to mention before I move on here is that when you do a two-sample t-test, it's going to ask you if you have pooled or unpooled data. We, in this class, are going to use unpooled data. And basically, that just means we're going to assume our groups don't have the same variance. Okay, pooled is essentially a fancy word for saying our groups have the same variances. Unpooled, we have different variances. So just to make things easy, we're going to use unpooled in this class. Again, if you go on to some other classes, they'll be a little bit more explicit about that distinction. So here's a typical question that would come up in light of the two-sample testing situations. So this says a researcher wishes to compare body mass index, BMI, for two different racial groups within the United States, and we're going to look at the ages from 20 to 39. The CDC gathered the data, and the results of the study are below. At alpha equals 0.01, is there enough evidence to reject the claim that the average BMI for both groups is the same? Now, what it gives us is it gives us two groups. And again, this is a CDC language. So CDC language has lots of groups. You can check it there. But one of the groups is non-Hispanic Black individuals. So we can look at their body mass index. And then we can look at Hispanic body mass index as well. All right. If you want to learn more about body mass index, you can look that up. It's basically a ratio of how heavy you are to your height. So there it is. So Black BMI, we have a sample average, we have a sample standard deviation, and we have a sample size. Hispanic BMI, we have a sample average, a sample standard deviation, and a sample size. Now, notice that I've already labeled these with subscripts. So basically what I'm saying is Black BMI, I'm calling group 1. Hispanic BMI, I'm calling group 2. All right, so that's what's happening. Now we're going to turn to a two-sample t-test. Why t? Well, because I have a sample standard deviation given to us. So we're going to utilize a two-sample t-test. Now, before we actually get into the t-test, the one thing that I haven't done yet is set this thing up. So I want to just show you that we're utilizing the t-test and why we're doing that. But let's actually start setting this stuff up. Let's start doing this. How are we going to set this up? Well, you'll notice that the inputs, or I should say the inputs, but rather the null hypothesis, alternative hypothesis is the test we're going to use. All of this layout is the same layout from chapter 9. So here's what we do. We say, well, alternative hypothesis, what's that? That is the statement, well, in this case, that is the statement that the average for group 1, so let me pick out the average for group 1 is equal to the average for group 2, okay? What's the alternative hypothesis? Well, if you remember, we're looking at are these two groups, do they have the same average or not? So basically, does the average for group 1 equal or does it not equal to the average for group 2? Again, I'm utilizing some quick keys, but there it is. Alternative hypothesis, average for group 1 not equal to the average for group 2. Again, we're using mu because we're talking about population average, okay? And all of that comes from claim that the average BMI of both groups is the same, right? Same or not the same? That's what we're doing. Now, we just said that we're going to use a two-sample t test. And so let's go ahead and do this. Now, I know you can figure this out on your own, so I'm not going to be insulting you or anything like that, but I do want to just make sure that we all know what we're doing here. So let me turn to my calculator once again. So take our calculators out. Stat, we know where that's at. Into the test menu. So excuse me about this. Into the test menu. Our two-sample z two-sample z is in 3. We're using a two-sample t, which is the 1 in 4. So that's what we're using there. When you click enter, you can see what you're going to type in. Now, just a quick note here. Notice that last line on my calculator says pooled, yes or no. We, again, are always going to use the unpooled characteristics. So that's what we're going to use, no unpooled. And then you can see the inputs there are average of group 1, standard deviation for group 1, sample size of group 1, and then you do the same thing for group 2. So put all those things in there. 28.4 is the average for group 1, 6.35 is the standard deviation for group 1, 404 is the sample size of group 1. Then he starts 29.3 is the average of group 2, 5.60 is the standard deviation for group 2, 385 is the size of group 2. And we're obviously going to choose the not equal to key. We're obviously going to, like I just said, choose not pooled, so no for pooled, and then calculate. And all of a sudden, I get a p-value just like I did in chapter 9. And so my p-value is 0.0348. What was my alpha there? I forgot what the alpha was. Alpha was 0.01. So this p-value is greater than alpha, and so we're good to go. All right, so we know what that means. That means just like before, p is greater than alpha. We do not reject the null hypothesis. And if I don't reject the null hypothesis, what I'm saying is that the average BMI for non-Hispanic Black individuals is close to the average BMI for Hispanic individuals within the United States. Okay? So notice that these are going to be a little bit longer statements. Just because of the nature of we're dealing with two groups. So we're going to have to explicitly talk about, or I shouldn't say talk about, we're going to explicitly list out both groups when we're talking about the interpretation statement. So it's going to be a slightly longer statement, but it's pretty much the same as what we had in previous chapters. Again, we're talking about averages. That's important. Average of one group is close to the average for the other group. Okay? Again, you might ask yourself, well, why are we talking about BMI of different groups, different races of people? Again, this is just something we found, so we figured might as well look at it. And again, this is not anti non-Hispanic Black people or pro non-Hispanic Black people. It's just a statement of fact, as statistical facts. Again, so we're trying to once again utilize, or I should say, demonstrate the stuff we talked about in chapter 1. You can look at differences between groups of people and not be offensive to any of those people. All right, so there you go. Let's take a look at example 2, and in fact, I'll show this using the overhead slide, although that's what we'll do. So I want you to read and then do the problem in example 2. Push pause on the video. I'll give about 10 seconds, and then I will unpause the video, or excuse me, I will do it on my own. All right, so let's go to this problem in on the notes. So, person claims average arm length for men is longer than the average arm length of women. All right. So again, we look at CDC data, and they looked at the upper arm length of males and females between, again, the ages of 20 and 29. So their data here we have in centimeters. We're going to test the claim that men have an average upper arm length which is longer than women's. All right, we'll use alpha equals 0.05. So once again, we're talking about averages. So what we do is we say the average for group 1 is equal to the average of group 2. That's my null hypothesis. I'm going to scroll up just a hair. Now, the key thing here in my alternative is that the claim is talking about is the average for men greater than the average for women. Now, notice that I put men as group 1 and women as group 2. No reason for that, just that's how the groups are laid out. So basically, what we need to do, my whole point of saying that, is to make sure that when you take the average of group 1, we know that that is referring to the male group, and the average for group 2, we know that is referring to the female group. Okay, so the average for men greater than the average for women. That's basically our alternative hypothesis. Now, once again, we're given sample standard deviations. So we want to use a 2-sample t-test. And in the same way we did before, we're just going to go back into our menu, stats, tests. 2-sample t-test is number 4. And then we're going to input the average arm length for men, the standard deviation for men, and the sample size for men. And we'll do the same thing for women. We are going to use the greater than symbol. And once again, we're going to say not pooled. So we're going to use not pooled. And all of that together, when I type that into my calculator, I get a p-value of, well, this is 0. Hopefully, you also got a p-value of 0. Now, what's a p-value of 0 mean? Well, quite simply, it is so small that your calculator doesn't even register it. So it's such a small number that my calculator registers it at 0. And we've seen before in scientific notation that your calculator can register some pretty small numbers, right? 10 to the negative 22nd, it registers and it can recognize. So that's a number which is so small that it's considered 0. So basically what they're saying is there's no chance that this null hypothesis can be true. P is less than alpha. We reject the null hypothesis. All right. Now, if we reject the null hypothesis, we say, yep, this is not going to be true. So think of it as crossing that out. Again, we don't have to write that on the test, but think of it that way. So what we're going to have to conclude is that the average arm length for males is in fact greater than the average arm length for females. Now, I think, actually, let me change that. I think they used men and women. Men is greater than the average arm length for women. I think that's the terms I used in the problem. So I'll keep that. Yeah, men, males, females, men, women. Doesn't, I guess they use both terms. So so there you go. The average arm length for men is greater than the average arm length for women, statistically speaking. Now, a lot of times what's going to happen is we're going to take an example and it's not going to have a nice, it's not going to have a nice table that gives me everything I want. More likely, it's going to look something like this, where the data is embedded into the problem that we're looking at. So what I'd like you to do is take a look at this problem, figure out how to test it, which test to use, and then go ahead and do the problem. Push pause on the video, try it, and then we'll come back. All right, so hopefully you've done the problem. If you haven't, make sure you do, okay? Now, the main part about this is that we get group 1 and group 2 correct. So there's no actual right or wrong way. We just need to make sure that if you say, well, CMU professors, we're going to call that group 1, and Western Michigan, WMU professors, we're going to call those group 2, then we stay consistent with all of our notation, okay? So the lawyer claims that there's no difference. What does that mean? That means that the null hypothesis is going to be that the average of group 1 is equal to the average of group 2, and that's the main claim. So alternatively, my counterclaim, my alternative hypothesis is going to be, that the average of group 1 is not equal to the average of group 2. Okay, if you're wondering how I'm typing that, that's just a little latex key. So there it is. Test. Now, which test should we use here? Well, we assume that we have a population standard deviation in each case. So we're going to assume a population standard deviation. That means I'm going to use a 2-sample z-test. All right, population standard deviations, we use z. Sample standard deviations, we use t. Okay, now you can imagine what we're typing in here. We go to stats, tests, the 2-sample z-test is there. Be really careful because the first entries are 22,000 and 22,000. Whoops. In other words, the first entries here are my population standard deviations. And then it asks me for the group averages. Now, again, be careful. Group 1 is CMU, so the average for salary of CMU for these 284 professors was 108,500. And the sample size is 284, so that's my X1 and my N1. My X2 is going to be 109,600. That's the average for Western Michigan with a sample size of 357. We're going to utilize not equal to. Notice that on the, on the 2-sample z-test, it does not ask me for pooled. You can't have pooled with a z-test. We can't assume the same standard deviations. So just as a quick look, hopefully your calculator looks like this. And we come up. Now, when I hit calculate, I get a p-value of 0.5295. Compare that to my alpha. Well, let's look up at the alpha's 0.05. So clearly, this is bigger than alpha. All right. So what's my conclusion? Anytime p is bigger than alpha, we do not, I almost said that wrong. Do not reject H0. We do not reject the null hypothesis. If you would rather, by hand write H0, if you would rather write null hypothesis, that's fine too. Okay. I tend to say shortcut is easier to write, so I tend to write H0 every time. Now, if we do not reject H0, what are we saying? We're saying the average salary of professors at Central Michigan University is close to the average salary of professors at Western Michigan University. Whoops. There you go. Sorry, that took, again, it takes a little bit long time to write, but that's what it is. Okay. So there you go. There's how to do the t-test, how to do the z-test. All right, so let's turn to example 4. I want you to push pause on the video and try to do example 4 on your own. All right, so what we have here, hopefully again you did this on your own and checking it up. So what we have here is, again, a professor's salaries, but this time we're comparing basically all the two-year colleges in Michigan versus just Mid-Michigan Community College or Mid-Michigan College. All right, so all in Michigan, I'm going to call that group 1. All right, I'm just going to put a 1 there. All in Michigan, we'll call that group 1. And then I'm going to call Mid-Michigan College. Professors there we'll call group 2. All right. Again, I just write that down so that it helps me when I start putting things into my calculator and doing all that kind of stuff. So, null hypothesis. Can we conclude that the average professor salary at Mid-Michigan College is below the Michigan average? So, all in Michigan versus Mid-Michigan College. So this college versus everybody in Michigan. Can we conclude that they're below the state average, it should say? So my null hypothesis, average of group 1 is equal to the average of group 2. My alternative hypothesis is that, oops, the average of group 1 is greater than the average of group 2. Now be careful with this sign here. Can we conclude that the average salary at Mid-Michigan College, that's the average salary here, and group 2 is below group 1. So if I'm looking at group 2 being below group 1, I need the symbol to go this way. Now, some people may have switched that. If you would have been somebody who said Mid-Michigan College is group 1 and everybody else in Michigan is group 2, you would have switched your symbol. Okay? So because I called group 1 everybody in Michigan, Mid-Michigan College I called group 2, I used the symbol that way. But if you, again, called this group group 1 and this group 2, you'd have had to flip your symbol. Okay, so be very careful when you're writing that symbol that we have it in the correct way. Okay. Now, the test I'm going to use is a 2-sample t-test. And that's because we have a sample standard deviation. In fact, I don't even need to have both, just as long as one sample standard deviation is what's given to me. So we're going to use a 2 sample t test for our test. And so we go back into our calculator, 2 sample t test. The average of group 1, again, group 1 is all in Michigan. So it's average salary of all in Michigan, 79,083. Standard deviation of all in Michigan, 21,560. Sample size of group 1 is 500. Group 2, average is 63,956. Standard deviation, 15,170. Sample size for group 2 is 35. Okay. We utilize the greater than, again, be very careful on that, and as always, not pooled. And what I got is a p-value of 8.34 times 10 to the negative 7th power. That is a really low p-value. So this p-value is definitely less than alpha. And so our conclusion, this is again a very small p-value, we reject the null hypothesis. All right? Rejecting the null hypothesis. Again, if I reject the null hypothesis, that means this can't be true. Just for sake of ease, I'll strike through that. So my alternative must be true. That means the average salary in the state of Michigan for professors at two-year colleges is greater than the average salary at Mid-Michigan College. So the average salary of professors, I should say two-year college professors, in the state takes a moment to write. But that's it. The average salary of two-year college professors in Michigan is greater than the average salary of professors at Mid-Michigan College. So there you have it. Again, normally what's going to happen, you're not going to write the actual strike through on the test. You'll just leave it like that, but you'll just think of it as, oh yeah, that can't happen, and so the alternative must happen. The null can't happen, then the alternative must happen. All right? So hopefully that all makes sense. Let's do one more before we move on to the other types of tests that are in this chapter. I want you to push pause and try example number 5. All right, so clearly what it's asking us to do is compare average production in terms of bushels per acre between North and Central Michigan compared to Southern Michigan. Okay, the data you can see there. All right, so here we go. Looking at this again, we have to determine which one's group 1 and which one's group 2. So I'll do North and Central Michigan. I'll call that group 1. And the Southern Michigan, I will call that group 2. Okay? Null hypothesis so far has always been the average of group 1 is equal to the average of group 2. The alternative, now our statement says something about southern counties producing more. So again, I'm looking at, are the southern counties producing more than the northern counties? So I guess I can just put northern counties. I think central covers the northern. So northern versus southern Michigan crop yields. So our sign needs to say, is the South producing more? Think about it like this. South producing more than the North. So my sign has to be a less than in my alternative hypothesis. The test needs to be a two-sample t-test. And that's, again, we have sample standard deviations. Most likely, we have sample standard deviations, all right? Again, the t-test is a more likely test than the z-test. So we go through and we turn to our t-test, our two sample t-tests. And so northern Michigan, north central Michigan, sample size was 28. That's the N1 is 28. Standard deviation, 22.7. My X bar should be 142.98. I kind of said that backwards. Hopefully that doesn't throw you off. So your inputs are 142.98 for your sample average, your 22.71 for your sample standard deviation, 28 for the size of your group 1. Your group 2 is going to have a sample average of 158.01, a standard deviation of 16.26, and a size of 27. The symbol needs to be the less than symbol because that's what we're looking at here in my alternative hypothesis. Once again, we use no for the pooled. And when you calculate that, you get a p-value of 0.0033, or I'm sorry, 0034 because it does round up to 4 when I round it to 4 decimal places. Now, my alpha is 0.02. This p-value is less than alpha. So my conclusion is to reject H0. Okay. So I reject H0, strike that through, pretend that doesn't work. We know H0 doesn't work. So the average bushels per acre in northern Michigan counties is less than the average bushels per acre in southern Michigan counties. So I saved you the wasted time of me actually typing it out, and I just typed it out on pause. So the average number of bushels per acre of corn in northern Michigan counties is less than the average number of bushels per acre of corn in southern Michigan counties. Now, just as a note, if you wanted to, you could have reversed that process. or that statement, and you could have reversed it and said the following. So you could have said the average number of bushels per acre of corn in southern Michigan counties is greater than the average number of bushels per acre of corn in northern Michigan counties. So again, northern is less than southern is the same as southern is more than northern. So you can say it either way. Now that's going to finish this video. We will start the next video and doing those other two types of tests we talked about for chapter 10, the two sample hypothesis testing.